Welcome to next session on design of counters. I think that after last few sessions, students must have been well exposed to the concept of how do we design a counter. What we want is that this is a decade counter. It is having 10 valid states from 0000 to 1001, and what we expect is that it has having 4 flip-flops, flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 3, and from current state, when clock pulse comes, the concept of design of counter is the current state of all JK flip-flops, flip-flop number 0 to flip-flop number 4, that is its outputs. What do we mean by state? Its outputs, Q0, Q1, Q2, Q3, and additionally we also have Q0 bar, Q1 bar, Q2 bar, Q3 bar. The current Qs should decide J's and K's such that when clock comes, all flip-flops proceed to next expected state. So for each flip-flop, input should be such that its next state, either 1 or 0, depending upon the current state, is defined. So what we do is all outputs Q0 to Q3 may be considered depending upon requirement to decide J and K's of all flip-flops. So as we have last time said that a flip-flop, the 0 always toggles. So since it is always toggling, its inputs J0 and K0 are kept 1, 1. So when they are kept 1, 1, it continues to toggle, and there is no variation from each time it is toggling. There is not a single variation. Whereas now, if we watch at Q1, what you find is Q1 continues, Q1 toggles, Q1 continues, Q1 toggles, Q1 continues, Q1 toggles. So Q1 toggles when Q0 is 1, 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 Q1 toggles when Q0 is 1. But most important thing which you need to consider is this situation from, let us say, state 9, it should advance to next state. Means here, each time when this was 1, you find this toggling. When this was 1, you find this toggling. But in this case, what you find is that if this is 1 here, but it continues. So when it should continue and when it should toggle. So for a state when this is now, in fact actually the detailed K-map design is not there because it is now assumed to be very simple, but I will still explain to you. When Q0 is 1, it toggles except when Q0 is 1 and these are 1, 0, 0. So if these are 1, 0, 0 and Q0 is 1, it should not toggle. So what I can say that J1 and K1 both would have been equal to Q0. J1 and K1 both would have been equal to Q0 except the fact that from 9 to 0 state, Q0 is 1, but these are 1, 0, 0. So what you can do is, listen very carefully, it's a very fundamental issue. Idea should be understood. You are not expected to design very huge digital system, but the concept. So if Q0 is 1 and Q3, Q2, Q1 are not 1, 0, 0. Listen very carefully. मराठीत सांगतो. Q0 1 असताना Q1 टॉगल झाला पाहिजे प्रत्येक वेळी एक्सेप्ट ज्यावेळी तो टॉगल न होता कंटिन्यू राहायला पाहिजे. म्हणजे J1, K1 should be Q0. When Q0 is 0, when Q0 is 0, they should be 0. When Q0 is 1, it should be 1 in all cases. Q0 is 1, here toggling expected. But when Q0 is 1, but if these are 1, 0, 0, for this case it should be 0. So only Q0 is not expected, but what is to be done is that J1 and K1 should be Q0 when Q0 is 1, it will be 1, but this should not be 1, 0, 0. Should not be 1, 0, 0 means what we would be requiring was should be 1, 0, 0. Q3, Q2, Q1 should not be, listen very carefully, I am explaining very simple words. Should not be 1, 0, 0. म्हणजे जरी Q0 1 असेल तरी जर Q3, Q2, Q1 हे 1, 0, 0 असतील तर J1 K1 1 होता कामा नये. म्हणजे when Q3, Q1, Q0 are 1, 0, 0, that time it should be 0 even if Q0 is 1. So this should be 0. We can go for alternative design also by using OR gates. So how do we go is not important. So what you can say additionally, in other words, Q1 continuous state when Q0 is 0. 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 Q1 continuous state even if Q0 is not 0, but these are 1, 0, 0. So if, listen very carefully now, so I can write J1 and K1 should be 0 when either Q0 is 0 or Q3, Q2, Q1 are 1, 0, 0. Means in both of these cases, this should be, if it is Q0, then it is 0. If this is 1, 0, 0, it should be 0. So what? J1 and K1 is equal to Q0 ANDed with Q0 ANDed with. This is Q3, Q2 bar, Q1 bar, whole bar. So now J1 and K1, you can test it for all possible combinations. When Q3 is 1, Q2 is 0 and Q1 is 0, Q3 is 1, Q2 is 0, Q1 is 0. Q3 1, Q2 bar 1, Q1 1, Q3 dot Q2 bar dot Q1 bar 1, it's bar 0. So when means when this becomes 0, this becomes 0 when Q3, this becomes 0 when Q3, Q2, Q1 are 1 0 0. When this becomes 0, when Q0 is 0. And it is ANDing, it is ANDing. So if any of them is 0, sum is, the product is 0. So if this is 0, it will maintain the state, and even if it is not 0 but this is 0, that is Q3 dot Q2 bar dot Q1 bar 0, in that case, that is, this is 1, it's bar 1, it's bar 1, it's product 1, it's bar 0. So when Q3, Q2, Q1 are 1 0 0, J1 and K1 will become 0, so that especially this one is maintained. So J1 and K1 is, this is not, I am not saying that this is the only way of design, there can be many ways also. Students may think both are same, Q3 and Q0 into Q3, Q1. You can simplify this also, but right now that is not our purpose. So we just focus on how do we design counters. The next we go for number 2. Flip-flop number 2 inputs, J2 and K2. What about J2 and K2? For J2 and K2 things are somewhat simpler. We find that flip-flop number 2, in which case it toggles, it toggles for designing flip-flop number 2 is simple. You just verify, continues, and here toggles, and here toggles. Now, intuition of human being is something different, which would be always a challenging task for AI developers, artificial intelligence developers. So, what especially, this is handwritten. You capture image with your eyes and you view three-dimensionally, and when you view at the board, you get a 2D view. So here, what your eyes notice automatically, that is very difficult for AI to do. What is clicked? When there is toggle, human beings' vision is capable. It is some intuition. The researchers may take their own time to define. Similarity or contrast in some things is easily noticed. So 0 to 1, toggling. What is similar in this entire thing is that without any much logic, you find when Q1, Q0 or 1, 1, that time toggling takes place, and at all rest cases it is last state. At all rest cases it is last state. So straight away you can say that J2 and K2 both are same. See, in counter, since the output is depending on the last state, either it will maintain or it will toggle. If you want it to toggle, you make J and K as 1. If you want to maintain, you make J and K as 0. So in almost all counters, unless you go for designing something differently, J and K are made common, and they are either made 0 depending upon, so JK of all flip-flops is made common, and you can even go for design JK equal to, as JK of each flip-flop is governed by Q of all flip-flops, maybe, or few flip-flops. Let us, in this case, you find it is Q1, Q0. It is Q1, Q0. Now, for Q3 it is quite interesting. For Q3 what we are finding? For Q3, maintain same, maintain same, maintain same. Sorry, for maintaining I have used this direction. On this side, maintain, 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 toggle, maintain and toggle. So there are two togglings. There are two togglings. This toggling is when this is 1, 1, 1. This is 1, 1, 1. This toggling is there. But this toggling, so if you say, just like a binary counter, if you can say that J3 and K3 equal to Q2, Q1, Q0, Q2, Q1, Q0, then this toggling will take place. But what about this toggling? This toggling. So, when this toggles, what is peculiarity here? So this toggling, so what you are expected that J3 and K3, now here there are total 10 states. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 transitions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of these 10 transitions, at 8 places, 1, 2, 3, 4, 5, 6, 7, 8, there is no toggling. So toggling is there only for two cases. Toggling is there only for two cases. What are the two cases? Toggling is there when these are 1, 1, 1, this one, and one more case is this. So what is, this is covered by, the first case is covered by J3 as well as K3. J3 and K3 both are same, equal to Q2, Q1, Q0 when these are 1, 1, 1. But here these are not 1, 1, 1. But here still toggling is there. What is special in this case, which is means what kind of logic you should apply such that it is there only for this case. Only for this case you find that this is remaining 1 only for 2 times. Out of that, this is 0 here, this is 1 here. So I can say plus Q3 dot Q0. You can simply verify. So the decade counter's most significant bit Q3 is expected to toggle if least significant 3 bits are 0, 0, 0, so are 1, 1, 1, or if most significant bit is 1 and least significant bit also 1. Then you can further simplify by taking Q0 common. By taking Q0 common, you can say Q2 dot Q1 plus Q3 into Q0. So there are many ways with which you can design. So in general, any counter you can design. Hex counter which advances through all possible states. If I am having n bits, then it advances to 2 raised to n states. Other than hex counter, what it does is decade counter. It can be mod 6 counter. Any number of counters, any number of states you can design. In that case, an n-bit counter contains number of states which are less than 2 raised to n. Which are less than 2 raised to n. So with this, I think there is no end to describe. Even we can have a skipping state counter, say only odd number counter, then prime number counter. We can, those who are really interested can think of designing, they can think of a prime number counter for numbers from 0 to 63. Prime number counter for numbers from 0 to 63, it would be a 6-bit counter, and it will advance from only prime numbers, say 2, 3, 5, like that. So it can be very interesting design. I think since the scope of this particular module in the entire syllabus is not so big, I have to curtail my discussion. I think we discussed more than what was required. All these counters are called as synchronous counters. Synchronous counters means in all these counters, whatever number of flip-flops we use, the clock given to each flip-flop is same, and we go for designing J and K of each flip-flop separately. We go for designing J and K of each flip-flop separately. Now I will mention one bit of asynchronous counter. Then after that we take a 2-minute break, and in the next video we will have shift registers, and that will complete the entire module of sequential circuits. That will complete entire module of sequential circuits. Now I will explain the asynchronous counter. In fact, it should have been other way around, but nowadays synchronous counter is so important. So asynchronous counter is normally now not so significant, because the question of designing with less resources is not that much relevant because of abundance of resources. In case of synchronous counter, clock to all flip-flops is same, whereas in asynchronous counter, I will just explain to you a 4-bit, a 3-bit I think is enough, a 3-bit asynchronous counter, very simply. Each is having Q, this would be Q2, Q1, Q0, JK, JK, clock, clock, clock. Now what is different between synchronous and asynchronous? What is the difference between synchronous and asynchronous? Just I will give a very interesting example which will tell what is the exact difference and what is the exact problem also. Suppose that on Saturday we will be having a IC test at some time, let us say 9 a.m. So since Friday is a weekend day, 9 a.m. on Saturday is something which is not so convenient time. So there is a need for waking up. That students should be awakened from the deep sleep in which they are thinking of various counter designs is very much required. So for that purpose, now let us say that alarms are not there. It's a fiction, just I am telling the story to impress upon you the concept of synchronous and asynchronous counter. Let us say that the students' clocks do not have alarms in their mobile. Students' mobiles do not have their alarms, but there is a centralized system. So case 1, now class representative. A class representative then somehow approaches a call center and tells that from your end you make bulk calls to all students. You make bulk calls to all students at 8 a.m. And when they receive the call, ask them, get up, your test, the most crucial IC test for Arduino based systems is going to start within an hour. So what will happen? All will get awakened up. Now case 2, CR says no, that taking call center help is not so required. So what he will do, he is very much sincere, let us hope, and he wakes up automatically at 8 a.m. Then you will say, oh, he doesn't have alarm. Oh no, he's so sincere that his body clock he has set so that he gets awakened at 8 a.m. Then he will call his friend. He will call roll number 1 and say, wake up and call roll number 2. Then roll number 1 will wake up and call roll number 2. Like this, when last roll number is called, it may take place that there may be 8:40. But in first case, when all are called from call center, all get a call at 8 a.m. This is the difference. So in synchronous counters, what happens is clock to all is same. So all flip-flops change the state simultaneously. All flip-flops change the state simultaneously. In fact, when I say simultaneously, there is small difference depending upon which flip-flop is fast or slow. When I get a call from call center, when the call from call center is there, depending upon my deep asleep state, one may get awakened within half a second, one may take 2-3 seconds. That may be the difference, but almost all get awakened simultaneously. So synchronous counters, all flip-flops, the change of state of flip-flop is at the falling edge of the clock. So all flip-flops change simultaneously. Whereas in asynchronous counter, clock is given only to the least significant. Clock is given only to the least significant flip-flop. And then, if I want a 3-bit up counter, Q2, Q1, Q0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0. So Q0 should always toggle, so I give clock to Q0 and I keep J and K of this flip-flop as 1. I keep it fixed. Now I find that all are toggling. All are toggling. So toggle. So what I do is say, I keep this as 1 and I keep this also as 1. So what will happen now? Each flip-flop will toggle when clock comes. Each flip-flop will toggle when clock comes. So this I want to always toggle. So I connect a clock directly. When this should toggle? When this should toggle? It should toggle. When clock comes, it should toggle. So in this case, this is not expected to toggle. Here it is expected to toggle. So when Q1 changes, that time it should toggle. So this is connected as, that is one output. Output of the least significant flip-flop is connected as clock. And when this should toggle? When this toggle, when this goes from 1 to 0. This goes from 1 to 0. This goes from 1 to, this should toggle. This goes from 1 to 0. So this Q1 is connected as clock to next flip-flop. So in asynchronous counters, clock is connected to only one flip-flop and outputs of the flip-flop, that is the least significant bit flip-flop, and clocks to other flip-flops are taken from previous output. So it toggles in this case, when this clock comes, that time this toggles. When this toggles, it will act as clock and then this toggles. So CR calling number 1 getting awakened, and then number 1 calling number 2. So there is a negligible but small time gap between the counter moving to next expected state. Means it happens so that this Q0 toggles, but it is taking time to toggle, and especially here Q0 toggles. In this case it is 1 Q0 is toggling, then it will take some more time for this to toggle, and then it is going to toggle this. So in asynchronous counter, if you observe this change, state was 0 1 1. Now clock comes. When clock comes, this becomes 0. When this becomes 0, this is expected to become 0. But when clock comes, this has become 0. This will make this. So there will be some time for which this continue, and then this will become 0. So in this case, this becomes 0. So this is very short-lived. Very short-lived. When this becomes 0, this is expected to become 1. So this will become 1 0 0. So from 0 1 1 to come to 1 0 0, there will be two short-lived, very negligible, but because of asynchronous things not happening simultaneously, the small non-required states, not expected states are there. This is asynchronous counter. I think we have talked much more than expected for counters. We will stop now. In the next lecture, immediately after 2 minutes, we will start for shift registers. Thank you.